Hello, students. Good morning. I hope everybody's doing well. The weather is nice, at least cool in the morning and maybe not too hot in the afternoon, but still that Houston area weather. Um, like I say before, the hard part about the COVID pandemic is that when people have the respiratory illness in the hot weather, it just makes everything so miserable. And I know even just when having congestion and things, it makes me feel really lousy. So hopefully before too long, we'll get back to a nice normal and cool weather and not too much variation. What I want to do today is just remind you that next week we'll have our third test, and I'll post an announcement about that by the end of the week. But that'll just cover the topics that we have been working on in trigonometry. So like I promised from the test that we did previous to this, I didn't include any of the trig just to make the stress a little bit lower to give you time to get more comfortable with the trigonometry. And what we want to do today is introduce the right triangle and talk about just the right triangle in terms of the trigonometric functions, at least defining the trigonometric functions of a particular angle in a triangle. We have that abstract concept now, so I want to say more about that. And then once we do some examples with the triangles, I want to show you how this particular interpretation is equivalent to the one that we've already been doing with the S1, the unit circle. So all of the arithmetic that we have set up, the reference number, that will become the reference angle, the sign conventions, Pythagorean identities, all of that will still be the same. But we will add some new dimensions that you'll see that we will get from the actual triangle. So if anything, what we do today is going to make the trigonometry hopefully a little bit easier. So let's go ahead and look at that. Let me get my, I had my IPvo up and turned on and then it went out on me. Let me get this up for us. Sometimes the technology is smart, it makes decisions for us. So let's see, I've got this, there we go. So let me share this. So right now, what we want to do is just look at a concept having to do with, like I say, just a right triangle. So this is going to be 6.2, and then we'll segue into 6.3. So I think you're going to actually like this. So we're just going to talk about right triangles. Now, the terminology and the labeling that we use for a right triangle or triangles in general is pretty lazy, and I don't apologize for it. That's basically how you learn geometry. So let's just draw a right triangle. So when we look at this, in this particular example, how we're going to label it will be fairly simple, but let's just notice here, when we have a right triangle in Euclidean geometry, we have the 90-degree angle, pi over 2 radians, and then we have two acute angles. The total sum of the interior angles for a Euclidean triangle is 180 degrees, or pi radians. So we will always use that when we were working with right triangles. Again, that's a very useful tool from Euclidean geometry. So we're going to make plenty of good use of that. Now, just for our use here, we're going to designate the abstract concept of the angle here to denote one of the acute angles. That is, we're going to call this the angle theta. So you can think of this as a center of a circle and then two radii coming out. And if you want to think about an arc connecting the two radii in a circle, this is the abstract concept of angle that we had before, that we found some way to actually connect it with the corresponding arc length, that is S equals R theta. So what we want to do is now think of the side that is opposite the angle theta, and we're going to call that OPP. When we label a side, mainly we're designating the side, but we're also letting the designation be the length. So it's a twofer, which is really sloppy, but that's what we do in math. So the OPP for now will correspond to the length of the opposite side. So again, these will be lengths. So we want to get 2 for the price of 1, which is what we do in mathematics. And then for the side that is adjacent to the side of the angle, we're going to call that ADG, or ADJ, excuse me, ADJ, and that will be short for adjacent. And then again, keep it simple. For the side that is opposite the right angle, we're going to call that hypotenuse, or HYP for short. Now, I'm not saying anything about equivalence to what we've already been doing, but we're going to utilize the concepts that we've already constructed. Again, when we think about tangent of an angle or cosine of an angle, we're going to use the constructs that we've already set up, but I'm not going to be fibbing to you. When we actually show the equivalence, then everything will be good and fine. I just don't want you to think I'm making things up. But we have to present this first for you to be able to make the transition. So what we're going to do is we're going to define the 6 trig functions relative to theta. So we're going to think about taking the trig function of an angle, which we've actually already been doing. So we're going to assume that this makes sense, at least for now. So we're going to say cosine theta will actually be the adjacent length divided by the hypotenuse length, or adjacent divided by hypotenuse. And again, by the Pythagorean theorem, these are going to be positive ratios because this is a triangle, but we're going to actually see that this definition can be no bigger than 1. So this is not going to give us something that's out in left field. Likewise, for sine theta, we will define it to be the length of the opposite side. So we'll write OPP divided by the length of the hypotenuse, HYP. So that's really the going out on a limb, so to speak. So again, thinking that we have the Pythagorean theorem or Pythagorean identities in the unit circle, we will have the corresponding Pythagorean theorem for right triangles. So that will actually come together in a very convenient way. Now, to cheat a little bit, we're going to define the remaining 4 based on how we did the definitions in the unit circle. So we're going to think of secant as being the reciprocal of cosine. So we're going to say secant theta will be the reciprocal of this. So this will be hypotenuse over adjacent. These ratios of sides turns out to be very convenient. And we don't want to forget this. So basically, just remember sine and cosine, and the rest will fall out in the wash. Now, again, we're going to think of writing the cosecant like we did before as the reciprocal of the sine. So that will be hypotenuse over opposite. So we're not being, ignoring the obvious here. We don't want to say, just be very just spontaneous about making definitions here and not being consistent with what we had before. So if we want to have any hope of doing what we had before, we've got to make the definitions consistent. So that's why we're doing this now. So we're thinking in the back of our mind that this would have to be this way. And then tangent of theta, we're going to think that's just going to be the sine theta divided by the cosine theta. So that would be opposite over hypotenuse divided by adjacent over hypotenuse. But of course, with this ratio, the hypotenuse terms absorb when we invert and multiply, just leaving us opposite over adjacent. So very good. And then of course, cotangent we will define to be the reciprocal of the tangent. So this will be cotangent theta will be adjacent over opposite. So when we think about these definitions, we went out on a limb for cosine and sine, really still thinking about the unit circle, basically. We're thinking about the x coordinate and the y coordinate. So this is not completely hideous, so to speak. And then when we look at the other four, we say, okay, well, we're just going to continue in the same trend that we developed for S1. Now, with an example of this, so let's just see how we can compute the trig functions with a simple example, and then we're going to talk about some special triangles. So say we have an example where we have a right triangle. Let's go ahead and draw a right triangle. And here's the right angle. And we're going to specify the theta to be this acute angle. And we're going to have a hypotenuse of 7 and a leg of 6. And so what we're asked to do is compute the 6 trig functions. So you're thinking, well, if this turns out to be equivalent, this will be a nice way to characterize the trigonometric functions. Now, first, when we think about this, we have the opposite side, we have the hypotenuse, but we don't have the adjacent side. This is the adjacent side to theta. But of course, this is a right triangle, so we have what we call the Pythagorean theorem, just like the Pythagorean identities from S1. So we have adjacent squared will equal the hypotenuse squared minus the leg squared. So this is just a difference of 2 squares. So this is what 7 minus 6 times 7 plus 6. So that's 1 times 7 plus 6, 1 times 13, or 13. So now, of course, we select the positive radical. Again, because this is a length, we get square root property gives us plus or minus, but we have a length, so that's non-negative. So we select the positive radical and get the adjacent side will be the square root of 13. So then we can go over here and say, well, we've determined this. I'll just write this in another color, square root of 13. So now we can easily write the trigonometric ratios. So we have cosine theta will be the adjacent over the hypotenuse. So I'll write some of these out for the cosine and the sine. So this will be square root 13 divided by 7. And sine theta will be the opposite over the hypotenuse, which in this case will be 6 over 7. Now, using the trend here, secant theta is just the reciprocal of the cosine. So that'll be 7 over square root 13. And then, of course, the cosecant will be the reciprocal of the sine That'll be 7/6. So what we're seeing here is that we're getting conventions that make sense as far as the ranges. These numbers are bigger than 1, so that's good. We need 1 or larger, or negative infinity to -1 in negative cases, but that won't happen with the triangles in the first quadrant, so to speak. So these are making sense based upon what we developed in S1. And then of course, tangent theta, that's just going to be sine over cosine. So we're going to have 6/7, in this case, divided by square root 13/7. So now what we see is that the 7's absorb, and we just get 6 over the square root of 13. So now the last one we need is cotangent. And cotangent of theta will just be the reciprocal of the tangent using the same rule that we established for S1. So we have cosine root 13/7. We have sine 6/7, secant the reciprocal here, cosecant the reciprocal here, and then of course tangent, the sine over the cosine, or adjacent over hypotenuse. See, what I'm doing here is thinking of it this way, but you're thinking, well, I'll just do adjacent over hypotenuse, or excuse me, adjacent over, sorry, I'll get it right. Opposite over adjacent, we'll just do 6/√13 to just do this directly. But you can always think about it this way. So either way you want to look at it, I don't want you to forget what we've already done, but now you can go directly to the triangle and just think what we've written over here, opposite over adjacent. So however you interpret things, it's all going to come together, because we're going to make sure that every interpretation is consistent. Now, let's look at some special triangles. What I did here in this particular case is to look at some examples. I've got some extra papers here. Let me move them out of the way. To look at some examples that you actually did in your high school days. And these were the special triangles. So let's look at a couple of them. So here's the first special triangle. So we're thinking, you know, we might as well remember this, since we're going to be talking about the right triangle interpretation of the trigonometry. So let's look at the 45-degree, 45-degree, 90-degree triangle. So let's draw it. So this is isosceles. That is, when you have the two acute angles equal, you get what we call an isosceles triangle with two legs congruent. So we'll just draw our easy right triangle. So if you like, I mean, it doesn't matter how we label it. We may go back and change the labeling as we work through the problem. But first, let's just start out with a side length of S in these two cases. And then maybe just H here in this case for hypotenuse. Sometimes we use H for height, and we will use that today. So we'll just kind of set it up this way. And then of course we have 45 degrees, or pi/4 radians in both cases. So again, degree measure is useful. Again, it's pure measure, but we have to remember, you know, to make conversions when necessary, especially when we're computing arc lengths. So now when we look at this, at least with this lettering, we have the use of the Pythagorean theorem. So we have S squared plus S squared is equal to H squared. And so that gives us 2S squared equals H squared. So now we've got these non-negative quantities, so we can use the square root property, but we can select the positive radical. So select positive radical. I mean, if you want to be completely, you know, meticulous, you'll say H equals plus or minus, but we can now be mature enough to know that this means that we will now have h equals the square root of 2. And of course, the square root of s squared is the absolute value of s. But of course, s is non-negative. So this is square root 2 times s. So what we're seeing here with the 45, 45, 90, so we can just write down the formulas. These are fairly user-friendly. And you see this triangle a lot, especially in engineering and physics. So we'll have this triangle, which I'll just go ahead and repeat right here. So just as a little note card type thing. So we have S, S, H, 45, 45. So we have this formula. H is the square root of 2 times S, or S is just H divided by the square root of 2. So that kind of completely identifies this triangle. And it comes up so much, we like to have it kind of in our back pocket because it's easy. Now, the other triangle that you used a lot in your geometry class had to do with the 30, 60, 90. Now, again, what I'm trying to tell you, ladies and gentlemen, is if you have these simple triangles, you don't really necessarily have to think trig functions. You can just go directly to these formulas. But again, you might say, well, I'm just thinking trig functions, Professor Ron, I'll just do it that way. But here's another special triangle. Sometimes it's quicker to have these in your back pocket because they're easy to remember. We'll have the 30 degree, 60 degree, and 90 degree. And you're thinking, well, this square root of 2, in this part of the pi over 4 radians, you know, we got 1 over root 2, 1 over root 2. That's where this is coming from. So this is not at all a surprise. And then with the 30, 60, 90, we're going to expect to have like maybe a 1/2 and a root 3 over 2. I mean, there's, again, not a surprise. So we're thinking, oh, these special triangles are just built in to the what? The unit circle. So they're already there. We're just kind of making light of them. So what we'll do in this case is we'll be a little bit more clever. Let's start with an equilateral triangle. And then we'll change up the formulas if we need to, or the way we designate things. So here we've got an equilateral triangle. So we're thinking we've got side length S all around. S, and we'll change this up a little bit later, but to make it more user friendly. So this is what we start with. Equilateral triangle, 3 sides congruent. So that means that with our degree sum, our particular angles are congruent. That is, these angles subtend congruent sides, and therefore we divide 180 by 3 and get 60. So we've got 60 degrees here and 60 degrees here. Now what we're going to do is drop the perpendicular bisector here from this angle. So this is just a construction. And so this gives us a 30-degree angle here and a 30-degree angle here. Now one thing that we notice with this, let me bring this up a little bit. What we notice with this triangle is that we have the Pythagorean theorem like we had before, but now we're thinking, okay, well, so how do we want to label this so we've got something good? So we move from here, and so let's just go ahead and take the part that's 30, 60, 90. So now this S we can just replace with H, because now, you can go ahead and put this here too. So we'll replace this with an H. And then the shorter side here, we can just call S for shorter. But now what we're seeing here is that when we do the perpendicular bisector, this is really already for free H over 2. So when you drop the perpendicular bisector, you just divide this by 2. So the shorter side for free is already the hypotenuse divided by 2, as long as this is the 60-degree angle and this is the 30-degree angle. Just taking this piece and moving over here. And so now, again, the angle opposite the larger angle, we will call L for longer. So we'll say H corresponds to hypotenuse, and we'll say L corresponds to longer side, and S corresponds to shorter side. Okay, so that's kind of like this, S, H, no problem. They're congruent, so you can use any label for S, no side shorter than the other. So there's nothing to be gained by changing that, but this does help. And so now when we look at this, we can apply the Pythagorean theorem. So this will be what? Hypotenuse squared equals the sum of the legs squared. So this will be H over 2 squared plus L squared. So we've got H squared equals H squared over 4 plus L squared. I know you've done this before. Maybe this is kind of dry and boring, but maybe it's a little rusty. And so now L squared, we'll just subtract 1/4 from 1. So L squared is 3/4 H squared. So now we will select the positive radical. Sometimes I just say select positive. So L is now the square root of 3 over 2. There's that square root of 3 over 2 times the absolute value of H. Equivalently, H is non-negative. So L equals square root 3 over 2 times H. So now we're thinking, okay, well, that's fine. So good. And then, of course, S is H over 2. And if we look at this, we could make a substitution. For instance, notice this is just square root 3 times H over 2. Just move the 2 over. And this is just square root 3 times S. So now we could say, okay, when we have this particular setup, we see that the side is just what? H, the shorter side is the hypotenuse over 2. The longer side is the square root of 3 times S, and that's really all we need. We can do the other, but it's kind of built in. So yeah, we got everything we need here. So you can make the substitution here. So that's good. There we go. So this will be for this triangle. This is 30, 60, 90. And also just for help here, like I did up here, we can just say that S will just be L divided by the square root of 3. So of course, if you replace H with 1, you just get the terminal points on the unit circle. I mean, like replacing H with 1 over root 2. So you're seeing that this is really part of the unit circle. We're just trying to build up to that. So again, not surprising at all. We had to work kind of hard to get the terminal points on the unit circle because we weren't using triangles. We were just using Euclidean distance, and that argument was much more complicated. Well, it wasn't hard, but it certainly wasn't easy like this one. Pythagorean theorem is like something you've seen since the 5th grade. So it's, you know, one of those things that you don't forget. And but I don't know. Everybody looks at things differently. So now let's see what we have here. Let's look at some examples. Let's just see how we can work with some special triangles, and then we'll move to less special triangles with angles that aren't very user friendly and see how that works out. But we will now assume that we are taking the trig functions of angles, and so we will treat those just like we do on the unit circle, and at least for now, accept the consistency that I really haven't verified as of yet. So let's look at this. Here's an example. So say we've got triangles within triangles. So we start out with this. So we've got a right angle here. So I'm going to drop a perpendicular. We've got a 60-degree angle. And then we're going to form a 30-degree angle here. So we're given this right triangle, and so of course that makes this, well, I'll fill that in, but then of course we're given this length to be 70 units. So that means that we have a 60-degree angle here. This is another right angle. We have a 30-degree angle here. So we've got an interesting setup. We've got right triangle outside and 2 right triangles on the inside. So that's an interesting little geometric construct. One thing about geometry is you can come up with all kinds of interesting figures, but the mathematics, the algebra has to support it. Otherwise, this drawing is fictitious. So we have to be careful that the number theory and the geometry, number theory, algebra, and geometry all work together. So here's what you're asked to do. You're given this label. That is, the length here is x. That is, that's a label. So that the problem is compute x. Now, again, this is really a problem that utilizes the special triangles. We don't have to worry about the trig functions if we don't want. So let's get some practice with the special triangles. So notice, in order to do this, we just need to find the length here and the length here. So if you like, I guess I can just label this with an A and a B. So we'll have this length to be A and this length to be B. So again, X is just the sum of A and B. So now we can think of this as a triangle, a right triangle, and then the second right triangle. And then of course the bigger one is the third right triangle, but I'm really not going to focus so much on that. I'm just going to make this problem as simple as possible. So in the first triangle, notice we have the angle 60 degrees. So this is the longer side. And then of course we have the side adjacent, which is the shorter. So we know A, the shorter side, is just the longer side divided by the square root of 3. We just showed that on the last computation. We did here, right here. Let me run the focus. Okay, so that's what we used. And then for 2, here, again, we've got the shorter side and here's the longer side. So again, when we look at the shorter side, we see that the longer side, we just flip this, is the square root of 3 times the shorter. So B will equal 70 times the square root of 3. So this is using, if you will, L equals square root of 3 times S. Equivalently, S equals L over square root 3. So that's what we just proved. So now this implies that X equals A plus B. So we have 70 over root 3 plus 70 times root 3. Now, I want to show you a couple of things here, and this is an exact computation. And then, of course, if WebAssign asks for a decimal approximation, you're just going to approximate the exact response. But first, we can look at this and say, well, you know, let's just factor this two different ways. You might look at this, and I think this is a good arithmetic exercise. For instance, here, why don't we just factor 70 times root 3 out of everything? So if we're thinking of just extracting this, then let's set up for that. So what we'll do is we'll write it in reverse order and then prepare for it. So we'll hit it with a root 3 over 3, root 3. So we'll do 70 root 3, and root 3 times root 3, that'll just be 3. So this kind of prepares for that. So multiply and divide by root 3. So we have 70 times root 3, and that'll leave the 1 behind here. And here, this leaves behind the 1/3. So this gives you 70 times root 3. And of course, that'll be 4. 4 is 3 plus 1, common denominator of 3, 4/3. And that gives you what? 280 root 3 over 3. So that would be one way to factor it. Well, say if you thought about it this way, here's another way to look at it. Say we look at this and say, well, okay, Professor Ron, I'm just going to factor 70 over root 3 and prepare for that. So let's do that. So we'll do 70 over root 3. So we'll do root 3 multiply by root 3 divide by root 3. So this will be 70 times 3 root 3. So now we're going to take out the 70 over root 3, which is all of this, and then all of this, kind of like what I did over here. We take out this and we take out this. So this gives us 70 over root 3. And of course, that leaves a 1 behind. And then here we're left behind with a 3. So this gives us 4 times 70 over root 3. But of course, if we rationalize, we get exactly that. So we get 280 times root 3 over 3. And I don't even care about rationalizing. That just happened to be rationalized, but WebAssign is fine with that. But how you choose to factor, it won't matter. There'll be times when you'll look at expressions and say, these have to be different. And the radicals and all will actually mesh in a certain way that you have to do some really interesting algebra to be able to secure the fact that they are actually equal. And that's why we need to practice with these types of calculations. Even though they're very simple, they're extremely important. And so now you can see that we attempted this problem just based on a special triangle. That is, we're back using the right triangle. So let's just use some simple ideas that we know about the 30, 60, 90 triangle. Now, with that said, let's look at another example. I have a couple here. So maybe we have a problem that is less user friendly. That is, we don't have a nice triangle. So here's an example. Here are two examples that allude to that. So say we have a lighthouse, I'll just draw a little lighthouse here. It doesn't maybe look like a lighthouse. Here's our lighthouse. And the lighthouse is 180 feet. And from the lighthouse, along the horizontal, we have a boat. You're in the boat right there. And we construct a horizontal, and we're given that the angle of depression to the boat, the angle of depression to the boat, let me write this out, angle of depression to the boat is 23 degrees. So we can put 23 degrees here. And the question will be, compute distance from the lighthouse to the boat. So again, a very simple problem. So what you could do is just denote this distance with the letter D. But now when you look at this, you've got basically two triangles. This also replicates D here. And then of course, if you're thinking, oh, so I could use this triangle, and then of course the height of the lighthouse is replicated here. Or then you're thinking, okay, well, let me just use this triangle. And so we could say, well, what's this? These are complementary. So we have 90 degrees minus 23 degrees, and that'll give us a 7. So that'll be a 67 degree angle here because they're complementary. So the idea, and of course we have our right triangle, a right angle here, like we have a right angle here. So when we look at this particular problem, what we're seeing is that the computation could use either triangle. So I don't guess it really matters. So you know, we bothered to get this angle here. So let's just go ahead and use this triangle, or you could use this one. It's your choice. But notice these are the angles that we have. We could, you know, now you know that that's a 23 here and that's a 67. So there are infinitely many ways to do this. So again, we could say, well, if we look at this angle and the positions of the sides, we have the opposite side of the 67 degree angle, and then we have the adjacent side. So here's the hypotenuse, so we have opposite, adjacent. So we can use tangent. Use tangent. So this will say that the tangent of 67, of course, this is a pure number, but we put the little O there, so you know it's a pure number in degrees, so not radians. So 67, tangent of 67 degrees will be the opposite over the adjacent. And that will give us D over 180. And so now if and only if, the distance D would just be 180 times the tangent of 67 degrees. Now, of course, you could just go ahead and convert the 67 degrees to radians, but our Google calculator will do that conversion for you when you need it. Excuse me, again, at this point, this is exact, but that's not the most user-friendly angle. Again, the tangent's defined for all real numbers as long as we avoid odd multiples of pi over 2. So now we can say, okay, let's get a Google approximation of this. So let's go to our Google calculator. Let me move this down so you can see it. There it is. So with the Google calculator, we want to make sure that we're using degrees. If you click on it and the degree is highlighted, or you don't really need to click on it, if you want radians, make sure it's highlighted. So that's highlighted. So we have 180 times tangent of 67. Again, assuming the compatibility with the previous definition. And that'll give us 424.053. And then in this particular problem, they say round to the nearest foot. So this will give us 424 feet as the approximate distance. So again, you see the beauty of the triangles, at least dealing with ratios. I mean, we could have done the 30, 60, 90 with tangent ratios, but I mean, it's easier just to use what we had already derived. But of course, in this particular case, we don't have special angles. They're not unit circle angles. And so we can actually, again, use the calculus approximation that the Google calculator will give us in giving us a very nice approximation for the tangent of 67 degrees. We know tangent of 60 degrees. Again, that's square root of 3. So we expect this number to be larger than the square root of 3 because it's an increasing function, but not by a whole lot. So again, we can always approximate things, but when you're asked to give an approximation on WebAssign, they won't accurate, and so they won't like a Google approximation that uses the infinite series to give you just expert precision. For instance, in calculus, I'll show you how to utilize an infinite series, and we can have enough terms in the partial sum to get whatever kind of accuracy we want. The thing is, the calculator doesn't add up an infinite number of terms. It simply adds enough terms to give us sufficient decimal accuracy. And since computers add really fast, they can add up, many terms. In some cases, they might only need maybe 6 or 7 terms if it converges quickly. So again, the calculator is just doing a lot of fast arithmetic that is based on an infinite series. Now, let's look at another example. Here, this one has to do with surveying. So I have a little bit extra room. Let me just go to another sheet and spread out a little bit. So say you're trying to figure out the height of a mountain and you've got your surveying equipment. So you're on the horizontal here. So here's an example. And this is kind of fun. I just thought we would do some fun triangle problems, just a nice break. Remind you of your engineering or your physics classes where you do math and you don't pay attention to what you're doing. Except use a fancy calculator, then wonder why the logarithm of a negative number gives you undefined. So here, we've got a mountain, which we will denote by this side, the height by this side. So that's a mountain. And you are surveying here, and you actually have surveyed to estimate an angle of elevation. So you have measured the angle of elevation here to be 32 degrees. And then you're thinking, okay, well, I want to figure out how tall the mountain is. I want to figure out the height of the mountain. So what you're going to do is you're going to think, well, I remember pre-calculus from Professor Ron's class, and so I need another angle of elevation. So here's what you decide to do. I'm making this a story problem, and I don't think it comes that way, but I guess it does. You move in another 1,000 feet and you measure another angle of elevation here at this point. And so this angle of elevation you measure to be 35 degrees. And here's our right angle, and we're going to let H be the height of the mountain. So here we'll say compute H Now, this is like the last problem. We want to get an exact answer, and if we need an approximation to the nearest foot or whatever, we can easily do that. But what we see here is that we got kind of close to 30, 60, 90, but no cigar, and we don't want to estimate. WeatherSign is going to require us to be more accurate than that. So what we want to do is first notice that we have this large right triangle. We're going to call that 1. And then we have the smaller right triangle here, which we're going to call 2. So when we do this problem, it's like, okay, well, let's go ahead and specify that this side of this right triangle, we can just denote by our favorite letter X. So we got to call it something because we're going to use it in our ratios. Now, from the computation, we can develop ratios that have X's and H's in them, and then we can actually maybe equate some things and then solve for the H. So this is not a problem that can be done the same way every time somebody does it. It just depends how you look at the equations. So what we're going to do first is look at the big triangle, so to speak. So we'll say here, for the larger triangle, again, we have an opposite side and an adjacent side. So again, we're going to use tangent. So we're seeing that this kind of quirky ratio of sides of a right triangle is turning out to be really, really useful. We're keeping our fingers crossed that it actually makes sense, but I'll go ahead and fib and say that not fib, I'll just say that it does, but we still are kind of hanging on a thread, so to speak. So we get the opposite side over the adjacent side. So tangent of 32 degrees will be H divided by X plus 1,000. So that's an equation right there. And now for 2, we can do the same thing again. We can use tangent again and get an equation that has H and X in it. So again, tangent of 35 degrees will be the opposite over the adjacent, or H over X. So now what we see is we can actually get 2 equations for H. So H equals X times tangent of 35 degrees. So we'll just call that 2. And then back to 1, if you want to cross multiply, H equals X plus 1,000 times tangent of 32 degrees. So we could call that number 2, or excuse me, number 1, just as rewriting the first number 1. So what we see here, and this is just one way to look at it, it doesn't matter how you do this problem, but notice that H's have equivalent expressions. So we can set the expressions equal, solve for X, and then of course use the simpler one to substitute here to get H and get an exact answer. And then we can get an approximation, calculus approximation using the Google calculator. So again, what we want to do is equate. Very simple algebra. The easy part was just using the tangent function, and now the algebra won't be any more difficult than what we've done here. So equate 1 and 2. So now we have what? We have, let's go ahead and multiply this, or just write it out, X plus 1,000 times tangent of 32 equals X times tangent of 35 degrees. So let's multiply this out. So we get what? X times tangent of 32 degrees plus 1,000 times tangent of 32 degrees equals X times tangent of 35 degrees. So now if you want, you can get all your tangents on one side and leave this alone. So we get 1,000 times tangent of 32 degrees and bring this over. So this will be x times tangent of 35 degrees minus tangent of 32 degrees. So again, subtract these two terms and factor the x. And so now we can get an expression for x. So x, if and only if, we just divide 1,000 tangent 32 divided by this difference. So we have 1,000 tangent of 32 degrees divided by tangent of 35 degrees minus tangent of 32 degrees. So that's x, and so now we're done pretty much. X times tangent of 35 degrees is h, so this implies that h just multiply by tangent of 35, so we get 1,000 times tangent of 32 degrees times tangent of 35 degrees divided by the difference. So this, maybe you're working for somebody and you develop this formula, and then you can say, well, here's a formula that will work. You give me the two angles of elevation. You could call one alpha and beta, and that number right there is the difference between the two positions. So you could set those as variables and say, well, here's a formula to figure out the height of a mountain under these circumstances. So it, you know, you could try to make a general formula if you like. I mean, surveyors are certainly much more happy with this kind of interpretation, just like if you were a plumber or an electrician, these types of calculations will be more helpful for what you need to do, unless you're, you know, a math major and you're trying to understand inverse trig functions and graphs, whereas the S1 is better. It really just depends what you're doing. So now this is what we call an exact answer. And so maybe you have a client that needs an approximation. So WebAssign in this problem says approximate to the nearest foot. Again, if it says approximate, approximate. Otherwise, that's the answer right there. I mean, that's the answer right there. That's the answer. The approximation, ladies and gentlemen, is not a better answer. It's a worse answer, okay? I, again, don't understand how you got into your brain that the approximation is the better answer. It is not. This is the exact answer. And so to keep all of our clients happy, we need to give them an approximate number. And it's important. I mean, it is important. I mean, mathematically speaking, it's less important. But you know, if you're building something, then you need to you need to measure something. You've got to get something tangible. So you would rather that whoever was doing the work had an exact answer, and then the only place they approximated was from this to the next line. And that way they can be assured that you have given them a good number. You have given them a good approximation. If your WebAssign's wrong with the approximation, then I can assure you you approximated in your route to that answer, and you built up round off error, which is messing up the calculation. So don't do any approximating. I mean, avoid it as much as you can until the final step. And so now we can go to our Google calculator, our good friend. And so now we can use parentheses upstairs. So we'll have parenthesis 1,000 English language. We love it, but it is difficult. I guess unless if we were trying to learn Mandarin Chinese, and then we'd have to learn alphabets and all that. So I guess we should be happy our language is pretty simple. And again, we're in degrees, so that's highlighted, 32. And then times tangent of 35. And now we want to divide by the difference, use the parentheses, the difference between the tangent of 35 degrees and the tangent of 32 degrees. Now, of course, you can use the tables. I've got tables on the web on the Blackboard site, but I like the fact that you can get a nice clean approximation. Just use it once in the problem. And this will give you 5,807, 5,807.6554. And we want to round to the nearest foot. So this will give us an approximate height of 5,808 feet. So this is what you want to share with your clients who are paying you good money for your expertise. As an engineer, as a future STEM professional, your boss wants to see this, and then you can go to here. Again, you want your work to be reliable, and at least this allows you, if you make a mistake, you can go back and check your work. You know, the nice thing about symbolic computation is that you can always check your steps. Maybe you just dropped a variable, maybe you dropped a sign. It's very easy to do, but if you've got this, you always have something to check. It's just like I'll be working something and of course, maybe you look at an expression one way and it just somehow gets confused in your mind and you see something that's not there. That happens when you're tired, of course. And so at least with this setup, you have something that you can depend on. And that's what we want when we do our calculations. Now, let's look to see why these triangles actually make sense. I don't think we were making anything up, at least anything that is going to keep us from moving forward. So let's see why these triangles actually make sense. And I'm going to show you, it doesn't take much time at all. So we're going to think of trig functions of angles, and the angle is going to take the place of the t value. The measurement along the unit circle here will be replaced with the angle, And reference angle, reference number, they all mean the same thing. There will be absolutely no difference between reference angle and reference number. All the arithmetic, the pluses and the minuses, the select positive, select negative, all of that stuff will be the same. We'll just have the additional information of ratios, which can actually, as we've seen, make some problems very doable and much simpler. So again, we're going to think trig functions of angles. Trig functions of angles. So angles replace measurements along S1. So the thing is, and remember, we've already developed that S equals R theta. And that was the connection between the measurement along S1 and the angle, the abstract angle. We proved that already. We got a nice definition. So let me move Professor Ron over so I can refocus. Now, what I want you to do is to draw an S1, and then we're going to take an R that's bigger than 1 and have concentric circles. So first, fix, in this case, R bigger than 1. So now, go ahead and draw some axes. So first what we want to do is draw S1. So we're thinking of a unit radius. So draw an S1. This is fun. I knew you all were probably getting wary of all the arithmetic and the inverse trig functions, but you know what, ladies and gentlemen, you got to know it. You got to know it. You want to survive calculus beyond just rote memorization, which ain't going to cut it. I want you to be prepared. My boss asked me today, he said, if we have a face-to-face class next term, would you like to come to campus? I said, I don't mind. I'd be glad to do it. He says, what do you want to teach? I said, I'll teach anything that's STEM. But it's interesting. I've done an open books course with the Shalm outline, Calculus 1, right here. See this? Shalm outline? That's the standard Calculus 1 book, Shalm outline. It was too hard. The students said, oh, this is too difficult, Professor Ron. I said, kids, this is the basic stuff. Go figure. And so now let's do a bigger R here. So we're going to make a larger circle, but concentric, same area or same center. So now what we want to do, so we've got is construct a radius that runs through both. Right there. So now this will be, we'll call this S1 and we'll call this SR or radius R, radius 1, S1 SR. And so the longer radius we'll just call R. And now terminal points, we're just going to say this one, we'll just call it PXY like we normally do on the unit circle. And we'll call this P1, which will be X1, Y1. So you're thinking, oh, I see the triangle starting to form, Professor Ron. They were always there, ladies and gentlemen. So what we're going to do, we're going to use the law of, this is a huge result, similar triangles. This is not easy to prove. I did this in a seminar one time and wished I hadn't. I mean, I said I should have proven the Pythagorean theorem to keep it simple. Just say that don't ever tell a group of students that something's easy when it's not. You don't want to get people to a seminar under false pretenses. But they understood that after that learning math is a journey. So the law of similar triangles is a huge result in mathematics. And basically it states the following: ratios of corresponding sides of similar triangles are equal. This is such a fundamental result. It's like the Pythagorean theorem. Without the law of similar triangles, we would not, well, let's just say there are two things that really create trigonometry: the Pythagorean theorem and the law of similar triangles. The absence of one of those makes all of this go up in a puff of smoke. So this is a huge result. So now what we want to do is drop the perpendiculars. Drop the perpendiculars. So these two triangles are similar. That is, we have angle theta and a right angle. And of course, these acute angles here and here are congruent using the 180-degree angle sum or pi radian angle sum. So these triangles are similar. We need that. And now we can simply notate these distances. This one is x. The longer one is x1. And then we have the distance y. I'll just do it on this side so it doesn't get in the way. And then y1. Right there. So this distance is y1, this distance is y. And so now we're thinking, okay, how did all of this start? Okay, well, by definition, cosine theta is the x coordinate on the unit circle of the terminal point, x. But that is just simply the adjacent side divided by the hypotenuse, which is x over 1. But these two triangles are similar, so ratios of corresponding sides are equal. So now x1 divided by r will now equal x over 1. And when we look at that, done. The idea is it doesn't matter what theta we use, as long as it's a theta that measures this angular distance, and it doesn't matter. So it doesn't matter what circle we use, the big circle, the little circle. It doesn't matter which triangle we use, the big triangle or the smaller triangle. It's immaterial. It doesn't matter what we chose for R. The law of similar triangles still holds. So the thing is that these were already here. We just didn't make any note of them because we didn't need them yet. Now for sine theta, that's simply on the unit circle, the y coordinate of the terminal point, which we choose to be y, but that equals y over 1, opposite side over hypotenuse. But by the law of similar triangles, that will now be y1 over r. So not only does the sine equal the y coordinate on the unit circle terminal point, it also equals the ratio of the opposite side divided by the hypotenuse for any triangle that's similar to this. So now we see the two interpretations are equivalent. So now you can think of any triangle any right triangle, theta, adjacent side x, opposite side y, and hypotenuse r, and we're good to go. So now we could say cosine theta equals x over r, sine theta equals y over r, etc. So the beauty is that this works because it's already there. And it's already there, but we need the extension to circles of different radii, which is covered by the law of similar triangles. So the key requires the Pythagorean theorem and the law of similar triangles. So this makes us, as we say, happy. Okay. So the key here is that maybe the first time you saw trigonometry, you started with the triangles, maybe. And then, of course, when you started to do graphs, they didn't make any sense. But now you can see that the angles, the reference angle really does make a lot of sense now, because you can't have triangles that have degree measures in the third and fourth quadrant. That doesn't make sense. The thing is that we can now still measure angles counterclockwise and angles clockwise, but this reference angle refers to a reference triangle. And so we have to think about the reference angle as being inextricably tied to the reference triangle. And then we can assign the pluses and the minuses relative to the coordinate where the theta or the t value terminates. So all of the arithmetic, ladies and gentlemen, is the same. We just have to be now careful that we've got ratios of corresponding sides of triangles, and all of our definition now can be supported by a new interpretation, which actually makes us more valuable to our employer because we have more understanding of what trigonometry actually is. So now we're thinking, well, let's use this newfound result. Let's now look for an alternative theorem about areas of triangles. So for instance, from high school geometry, and you know, geometry is important. It's like the calculus. Why am I lowercase letter? Professor Ron, that's not good. From high school geometry, we prove the area of a triangle is 1/2 base times height, where again the base is denoting the length of the base and the word height is denoting the length or the height of the length of the height. So sorry, times 1/2. So we're thinking, can we improve upon this from a more trigonometric standpoint? And absolutely we can. There's Heron's formula will be another improvement on this, but that's going to have to wait a little while until we have a little more structure. And so, for instance, we can have a little theorem here. We can say this, consider a triangle with sides A and B and an included angle theta. So let me just draw one case of this. So we have a triangle with sides A and B and an included angle theta. So this would be like a case one. Let me just give you a description of what this would be. When we say included angle, we mean just that. So say we have a side length A and a side length B, and we mean included in that this basically describes the vertex angle in the sense of thinking that's the center of a circle and you've got radii coming out. That's how we define the abstract angle, because we can tie it into what? Distance along the unit circle. That's how we define an angle from a unit circle. And then we abstract it to any polygon, not even triangles, but any polygon for that matter. So this is what we have, at least in terms of a description. Then the area of the triangle is, and not a surprise, 1/2 A times B times the sine of the angle. So we're thinking that looks just like this formula here, Professor Ron. So if we were going to actually show that this was valid, and it's easy to use, again, it doesn't matter how we define theta. If we're using theta in a trig function, the output's the same. I mean, as long as we're making sure that if we're utilizing our computation, our unit circle, we've got good information, or if we're using the Google calculator, we have the right mode, so to speak. So the idea in this particular case is that we could have triangles that are acute and we could have triangles that are obtuse. That is one angle that's greater than pi/2 radians or greater than 90 degrees. So this first case is the acute triangle. Acute triangle. And so we think, well, how do we find the area of an acute triangle? So we think, well, same song and dance before, drop the perpendicular like you did in high school geometry. I always enjoyed geometry. I like doing the constructions the best. That was fun. Yeah, my teacher, she gave me an A on my instructions, but she put a little dash by it, said, excellent job. So I thought the dash meant A-, and I asked her, I said, why did you give me an A- and then say excellent job? Oh no, Ron, no, Ron. That's just a dash for English. And so I said, well, could you please mark it out? And she did. I remember that like it was yesterday. Her name was Joy J. McDuffie, and I love that woman. She is a precious angel in my life and taught me the love of math. And to this day, I think about Miss McDuffie when I teach my classes. She was a blessing. So let's think about what we can do here. For instance, we can call the height of a triangle H and now use some trigonometry. So for instance, we have opposite over hypotenuse. So this implies that sine theta, so this is where these ratios of corresponding sides make sense. So opposite over hypotenuse, let's write it out. Opposite over hypotenuse. And that will be H over A. And so we can solve for H, the height, so that'll be H equals A times sine theta. We're thinking, well, we wish all proofs were this easy, but now we see that with this second interpretation of the trigonometry, then we're like, well, hallelujah, that's so simple. Now we can just use the formula. So this implies that the area will be 1/2. And now, of course, here's the base right here. Just go ahead and mark it off. There's the base, B. So we get 1/2 base times A sine theta. And then, of course, we make it look nice because we want to put it in a book. So we have 1/2 AB sine theta. So what we're seeing is that at least for case one, the result is just based upon the sine function, which obviously it has to be. I mean, why did I take the sine here? Because it's in the theorem result. So that at least gives me a clue as to how I should try to show that this is valid. Even though it's very simple, it's a good proof. Now, what's the second case? Again, we want to make sure that this is valid. You know, we're using this new freaky idea where Professor Ron has told you that reference number and reference angle are synonymous. They mean the same thing. So basically, let's draw an obtuse triangle. So we just want an obtuse angle. So obtuse triangle. Now, if you like, it doesn't matter. We can call this A and call this B, and there's the included angle. So again, two sides of a triangle and included angle. Now, of course, we want to extend side B so we can drop the perpendicular, because we can't really drop the perpendicular inside the triangle like we did here. And so we can do it now. But now what we're seeing here is that this angle will be defined based upon theta. Theta lives in the second quadrant. So this, what does that say? This implies that theta hat will now be pi minus theta. This is the reference angle or reference number if you like. But remember, sine theta is in the second quadrant, it's positive. So this implies that sine of theta equals sine of theta hat. Again, they're equal in terms of ratios of sides of triangles because the reference number, again, is built upon that of the second quadrant where the sign is positive. So the value is the same. So there you have it, that reference number, reference angle, extremely important. So here, if you like, just put theta hat. And so now, let's just call this what it is, H. So this implies that, okay, sine of theta hat will be opposite over hypotenuse. So H over A. But again, sine of theta hat is sine of theta. So we get the same thing, solving for H. H is A sine theta. So now we're thinking, okay, well, we're back to square one. We got the same formula. So this implies that area is just 1/2 base times height. So just fill it in, 1/2 base, here's a base, base times height, A sine theta, or 1/2 AB sine theta. So now you have a new way to characterize the area of a triangle that gives you more power. So maybe you don't have a special triangle where you have more knowledge about it, but you do have what we have here. That is two sides and an included angle. That at least opens the door to the computation of the triangle area. So now we can see that this can be of use to us later. We'll find many uses of this theorem, especially in trigonometry, and it's very useful with Heron's formula. So often in trigonometry, is just like in calculus, you're thinking, when are we ever going to use this? Well, then the second you say that, the next day you've got to use a concept that you learned and thought you'd never ever need again. And that's the thing about pre-calculus. You can't really leave out anything. You need to learn lots of different topics to be ready for the calculus. You need to know basic geometry. You need to know basic trigonometry. You need to know basic conic sections and sequences and series. And you need to know function transformations and even odd and college algebra. I mean, there's all kinds of stuff. And when I say basic, that pretty much means the foundation, which is most of it. So, lo and behold, like anything's any different from day one. So we have this nice formula, which we're going to use. So remember, two sides and included angle. Now, I want to do an example that mimics what you did back in chapter 5. But now we have the luxury of a triangle. And so you might say, Professor Ron, I don't need triangles unless I need a triangle in the problem. And so I can agree with you. It's kind of like on the very first problem here when we were talking about where was it? There was a situation where I was doing some ratios, kind of going back to the beginning. You can always think of sine over cosine, or you can think of opposite over adjacent. It just depends how you look at it. So your mode of working through a problem may differ from your colleague, but if you're using the same consistent concepts, it doesn't matter. The result will be the same. So let me just show you a problem that you already know how to do. And if you want to exercise new ideas with this, be my guest. So cosine theta, in this case, equals the following. That is 5 over 11. So that's legitimate. And we're given that sine theta is less than 0. And what we want to do is compute remaining trig functions. Compute remaining trig functions. Now, if we just analyze this a little bit, we see that the cosine is positive, the x is positive, but here the y is negative. So where x is positive and y is negative, that's fourth quadrant. So this basically says x is positive, y is negative. So this implies theta lives in the fourth quadrant. Okay, so that's really what we've done before. Nothing new there. We could say t value if we're on the unit circle, or we can say theta, and we know how they're related, s equal r theta. So we're thinking, okay, well, Pythagorean identities is what we did before, but now we know that cosine theta, in this case, is just x over r. Thinking of adjacent over hypotenuse, and this equals 5 over 11. So we can use the ratios. So equivalently, x equals 5, r equals 11. I mean, we can't reduce this. We could if we wanted to. The only thing that matters is the ratio. So now this will imply, using the Pythagorean theorem, just like if you were using the Pythagorean identity, we'll have y squared equals r squared, 11 squared, minus x squared. Let me turn I don't like when the email dings. I need to turn the monitor down. That's annoying. And then we're thinking, okay, well, this is what? 11 minus 5 times 11 plus 5. Just doing the difference of two squares. So this will give us what? So that's a 6 times what? A 16. 16 is a perfect square. So that's fine. That's just 4 times 4, 2 times 3, no perfect squares there. So now, of course, y is negative. So we select negative radical. So this gives you a little leg up. It's still the same computation. There's no difference. There really is no difference. It's equivalent. So now we see that y will be the square root of this with a negative sign. So this will be negative 4 times the square root of 6. So again, the square root of 16 is 4. So we get negative 4 times the square root of 6 by hypothesis. So now we have x, y, and r. We're done. So sine theta is just y over r. So that gives us negative 4 root 6 divided by 11. So you might think, well, this is a little bit easier because we're thinking about a triangle and you could draw a reference triangle if you wanted. But you got to keep the sign convention right. Don't be drawing triangles that have negative sides. That doesn't make any sense. Don't do that. You do it like this. And then cosecant of theta will be just the reciprocal. So negative 11 over 4 root 6. So that's pretty simple. Now we've got cosine, so we can get secant. So secant theta will just be the reciprocal of cosine, which is 11 over 5. So though some things are a little different, most everything is the same. And so now tangent theta will just be y over x, opposite over adjacent. So that will be negative 4 root 6 over what, 5. Just follow the x in there, the y's. And then, of course, cotangent is the reciprocal of tangent. So that doesn't change. And that'll be a negative 5 divided by 4 root 6. So the idea here is that this particular interpretation we've already seen in action. We already see how valuable the triangles are. But this kind of computation just means, okay, draw a reference triangle. Draw a reference triangle. So if you looked at this, you could say, okay, I'll draw a reference triangle. And so you've got 5, you've got 11, and you have 4 root 6. And then you can attach the appropriate sign. There's your reference triangle right there. So that gives you exactly what you need. So if you want to think of it that way, you really don't need to. You can just kind of do it this way, but you can kind of look at that. Often, a lot of times, a reference triangle is very useful just to keep everything coordinated, so to speak. But you can see how simple it is, because again, where's that paper? Right here. You see, they were already there. They're already staring at us. We just didn't notice them. Well, maybe you did, but we didn't acknowledge them. Okay. So now let's look at an example. What I want you to do as extra, we can just do it now quickly. I think we got enough time. So derive a formula. Now let's see what we know. Derive a formula for the area of an equilateral or equilateral triangle. So this is like a little, we can think of this as a lemma. And so we're good to go. Let's just draw what we drew before. That gives us the 30, 60, 90 triangle. So we can just, we don't have to do this, but sometimes it's good just to draw a little visual. Of course, geometry with the shapes and things are always helped by having some kind of way of looking at things. So again, remember, this is side S, and we've got a 60-degree angle. So that's really how simple it is. So now we can just say, okay, we have two sides which are denoted by S, and we have an included angle. So we'll say two sides, and an included angle. Now, of course, we can use other procedures here, but since we went ahead and derived a formula for the area of the triangle using trigonometry, let's use it. So this implies area. So now this is easy. Will be 1/2 AB, so S times S times S times the sine of the included angle, 60 degrees. So that's going to be 1/2 times S squared. And of course, sine of 60 degrees is sine of pi over 3. That's just root 3 over 2. So that gives us square root 3 over 4 S squared. So, so that gives you a nice handy formula. You don't even need our new formula for this. You can derive this in other ways, but now you can see if you have an equilateral triangle, you just hit the side squared with square root of 3/4. Now, maybe you won't remember that, but you could easily derive it. So now we see that with the utilization of the last theorem about the area of a triangle, we can come up with nicer formulas that may have required different means earlier. So whatever you think of that, again, as we have more and more elaborate theorems, they will have more application. And in some cases, we're thinking, you know, the most difficult theorems should be the ones where we're given the least desirable parts of a figure to determine an area. So the idea is that this is still fairly user friendly, but we are not often given angles and all that. And so, of course, when we get back to the inverse trig functions with the next lecture, we'll have a way to actually uncover angles, the reverse path, like we've talked about before. And that will be a huge plus to our computational ability. So again, the inverse trig functions will turn out to be very compatible with our right triangle approach. It's just that when we started talking about them, we needed to focus on mainly the unit circle to make sense out of everything. And now we're going to transition to the right triangles and see that there is some additional information to be had that will help us out, especially with reference right triangles. Now, here's another example that will allow us to use our new area formula, and it goes like this. We've got a circle. So just go ahead and draw, try to draw a freehand circle. You know, just get, you know, do 4 points in the center. So it's just like it's like you're sketching basically. In a lot of times, you know, as an undergraduate, our professors would have what they call French curves, which were these malleable rubber type curves that had reinforced with some type of metal. It's very beautiful objects where they would use the French curve to form certain shapes on the board to draw beautiful shapes. So yeah, we're not using a French curve. So we're kind of like, you know, in the deep end. So here's our circle. And what we have, we've got a central angle of 120 degrees. So we have 120 degrees. And we have radius in this case of 6. And then we actually draw a chord connecting these the endpoints of these 2 terminal points here. Or we got this angle and 2 terminal points. Or actually depends on how you're tracing this angle. Did you go here or did you go here? So we'll refer to them as terminals. And then we do this. So the problem here is compute area of shaded portion. Now, lots of times when it comes to computing areas and things, you know, you use your knowledge of trigonometry with triangles, You use all kinds of ideas that you may not put together often, but circles and polygons and things are very popular in geometry, and so especially in trigonometry. So we'll have more opportunities to do this and triangulate things and figure out areas. I think we'll enjoy that. And there's some nice WebAssign problems that we will work with those types of ideas. And there, again, I look forward to those. Now, when we look at this, we're thinking, okay, well, this is area is just the what? The difference between the sector area and the triangle area. So we'll say shaded area will be the sector area minus, in this case, the triangle area. So the sector is just a piece of pie, so to speak. It's all of this. The triangle is this. And of course, the difference between those two areas will give you the area of the shaded portion. So now let's just remember that what is this? We have too many equals. Let me get rid of this. So the sector area will be 1/2 r squared times theta. But of course, we need theta in radians where we're not attaching a trig function to it. So in order to have pure measure, this is pure measure, but it's not the pure measure we need. We made it up, and so it's not intrinsic to the geometry. So we have 120 degrees times pi. And of course, we don't need degrees here. These are pure numbers, so we're okay now that we're doing the conversion. This will just be 180. Again, degrees are pure measure in the sense that we deal with them as numbers, but the conversion goes this way. So we don't say pi radians, we just say pi as a pure number. So this gives us 1/2 r squared theta minus the triangle area will be 1/2. And of course, the included angle is 120 degrees, and the two sides are both of length 6. So this will be 6 times 6 times the sine of 120 degrees. And we can go ahead and convert that if you like. Doesn't matter, either way. Since we're using radians, we'll go ahead and work that through. So now notice we have the 1/2 6 squared in both of these, so we'll go ahead and factor. We have 6 times 6. And of course, the 2 divided by 3 divided by 60. So we have 2/3 pi. And then of course here we have sine of 2/3 pi. But of course, this is in the second quadrant, so we do the sign of the reference number. Again, same sign, both plus. So 2 into 6, that'll give us a 3. So 3 times 6, 2 pi over 3, minus sine of pi minus 2 pi over 3, just using the reference number or reference angle. So this gives us 18, 2 pi over 3, minus sine of what? Pi over 3. And of course, it's easier to use the trig functions in the first quadrant because that's where it all basically began. And so now we're good to go. So this gives us 18 times 2 pi over 3 minus square root 3 over 2. Sine of pi over 3, terminal point is 1/2 root 3 over 2, and we're good to go. So this is exact. Now, of course, if the problem requests an approximation, then give an approximation, but work to the exact answer as we always do, and then approximate. So what I want you to see here is that nothing's really changed. We just added some stuff. We've added these triangles and ratios of sides of right triangles where we thought, well, how does this have anything to do with the unit circle? And we see that they're all inextricably tied together. They're one kind of comes with the other. But what we're seeing is that there are certain approaches that are made more understandable with, or certain problems that are made more understandable with one approach over the other. That is, it's easier to think about inverse trig functions with the unit circle. It's easier to think about solving problems in geometry, surveying problems, etc., using triangles. So again, we're just building the foundation so that we can be more flexible when we come to mathematics. You'd be surprised that sometimes in mathematics, the reference triangle is extremely useful, especially in calculus 2. So we have to be good with both. And that's really what I'm trying to emphasize here. Now, next lecture, we'll talk some about the inverse trig functions and how they basically innervate all of this. What extra information do we get? Do we get anything new? A few things. And we'll talk about that. And then we'll move on into the law of sines, which will give us some more understanding of triangles, even though you're probably going to be very tired of triangles by the time we get to chapter 7. So thank you for your attendance today. Hopefully this work will give you a little bit more leg up on the trigonometry, as it possibly reminds you of some things you did in high school. And if it did, that's a good thing. If not, no bother. We start from scratch. So everybody have a great day. Again, thanks for your attendance. And if I don't see you at the conference hours, I'll see you on Thursday. Bye, everyone.
Thank you.
Bye. Thank you. Have a good day.
Thanks a lot, everyone.